Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the last lecture, we have discussed how we can obtain an absorption spectrum. We had mentioned that if we plot absorbance obtained from a spectroscopy experiment against wavelength lambda, we can obtain an absorption spectrum. Although conventionally absorbance is plotted against wavelength, we can also plot absorbance against frequency, as these are interchangeable. So, we can write h nu equals h c by lambda. Moreover, we can also plot absorbance against wave number. Wave number is denoted by nu bar, and nu bar is related to frequency because h nu equals h c nu bar, or we can write nu equals c nu bar. So, the next question is, what is the unit of nu bar? Because we can write nu equals c nu bar, or rearranging this equation we can write nu bar equals nu by c. So, we know the unit of the left hand side is equal to the unit of the right hand side. So, in order to find the unit of nu bar, we have to find the unit of the right hand side, and the unit of the right hand side is unit of nu by unit of c, that is 1 by second by centimeter per second. This gives 1 by centimeter or centimeter inverse. So, centimeter inverse is the unit of nu bar, and also lambda is normally represented in the unit of nanometer. So, let us look into the relation between nanometer and centimeter inverse. So, let us say the wavelength lambda equals x nanometer. So, in centimeter inverse, the wave number will be 1 by lambda, that is 1 by x nanometer, that is 1 by x times 10 to the power minus 7 centimeter equals 10 to the power 7 by x centimeter inverse. Later, we will discuss about different forms of spectroscopy like UV visible spectroscopy, infrared spectroscopy, microwave spectroscopy, and we will see that we get different spectroscopies depending on the wavelength of the light or the frequency of the light interacting with the matter. Conventionally, when we plot a UV visible spectrum, we use wavelength in the x axis. However, when we plot an infrared spectrum, conventionally we plot wave numbers on the x axis. This is just a convention used for convenience, such that the values plotted on the x axis are not very large numbers. So, let us see what do I mean by that. For example, 1000 wave numbers is a typical IR frequency. So, if we convert this number into nanometer, it will be 10 to the power 7 by 1000 equals 10 to the power 4 nanometer. So, 10 to the power 4 is a larger number than 1000. Similarly, 10 wave numbers is a typical energy gap involved in a microwave transition. So, this amounts to 10 to the power 7 divided by 10, that is 10 to the power 6 nanometer, which is a very, very large number. So far, we have explained the absorption process by saying we have a molecule in a stationary state of energy E 1, and when light of energy equals h nu 1 2 interacts with the molecule, then the molecule goes from the stationary state with energy E 1 to another stationary state of energy E 2, such that delta E or E 2 minus E 1 equals h nu 1 2. Apparently, only one frequency is involved, that is nu 1 2 in the transition process. Or in other words, in terms of experiments, if we use a polychromatic light source, that is light having many frequencies, we can expect that only one frequency, that is nu 1 2, should be absorbed by the matter. So, in all other frequencies where light is not absorbed, absorbance is given by A equals log I 0 by I t, and because in the other frequencies light is not absorbed by the matter. So, I t for those frequencies will be equal to I 0. So, absorbance we can write log I 0 divided by I 0 equals log 1, that is 0. The absorbance should only be non-zero at the frequency nu 1 2. So, this can be represented in a spectrum. So, again we are plotting absorbance versus frequency, and let us say this is my frequency nu 1 2. So, for all other frequencies the absorbance will be 0, and only at nu 1 2 the absorbance will be non-zero. However, it has been seen from experiments that the spectroscopic lines are not as infinitely sharp as shown in the plot, but they are more or less broad. Additionally, we should realize that as the light source is polychromatic, that is, the light consists of many frequencies, thus multiple transitions can be obtained from the same sample. So, this is a spectrum where the lines are associated with the antisymmetric stretching mode of carbon dioxide. At high resolution, the spectrum seems to consist of multiple lines from multiple transitions. So, if we expand the scale or if we zoom into one particular line, the line with apparent narrow feature is observed to have a definite width and a characteristic shape. The shape of the line spectrum is known as line shape. As this shape is a function of frequency, the line shape can be represented using a line shape function, which is given by f nu minus nu 0, where nu 0 is the frequency corresponding to the maximum absorbance. So, nu 0 is also known as the peak position. For a single peak corresponding to a transition, the shape of this spectrum is symmetric with respect to nu 0. So, the observation of the width and line shape from the carbon dioxide spectrum immediately raises two questions. One, what are the possible functional forms of these shapes? And number two, what physical processes are responsible for these shapes? Line shape functions fall into one of the two general categories. One is homogeneous and the second is inhomogeneous. A homogeneous line shape occurs when all the molecules in the system have identical line shape functions. Here, we should understand that we have an ensemble of molecules in the sample solution on which we shine light during the spectroscopy experiment. So, let us say we have made a sample solution of concentration equal to 0.1 molar, and let us say the volume of the container which is placed in the direction of light, so that the light is passed through the container and goes to the detector. So, the volume of this container is 1 milliliter. So, we know that for 1000 milliliter of sample with concentration equal to 1 molar, we have Avogadro number of molecules, which is approximately equal to 10 to the power 23 molecules. But now, in our solution, we have a volume of 1 milliliter and a concentration of 0.1 molar. So, the number of molecules we have during the experiment is 10 to the power 23 divided by 10 times 1000 equals 10 to the power 19 molecules. Thus, if all the molecules are affected the same way or are homogeneously affected during the light matter interaction, they will have the same line shapes and we will have homogeneous broadening or homogeneous line shape function. For example, if the absorbing species in the gas phase is subjected to high pressure, then all the molecules are found to have an identical pressure broadened line shape for a particular transition. Pressure broadening of a transition is thus said to be a homogeneous broadening. In contrast, if the sample is dissolved in a liquid solvent, then disorder inherent in the structure of the liquid provides different solvent environments for the solute. As each solute experiences a slightly different environment, they have a slightly different spectrum. The observed absorption spectrum from the experiment is made up of all the different spectra for the different molecular environments, and it is said to be inhomogeneously broadened. In general, the homogeneously broadened spectrum can be represented by a Lorentzian. So, the Lorentzian line shape function represents homogeneously broadened spectrum. The Lorentzian line shape function is given by f nu minus nu 0 equals 1 by pi gamma by 2 nu minus nu 0 squared plus gamma squared by 4. So, here gamma is the parameter specifying the width of the spectrum. The inhomogeneously broadened spectrum is given by a Gaussian line shape function. And the Gaussian line shape function can be written as f nu minus nu 0 equals 1 by sigma root over 2 pi e to the power minus nu minus nu 0 squared by 2 sigma squared. Here sigma is related to the width of the spectrum. So, we can quantify width of the observed spectrum in terms of full width at half maximum. This is also written as f w h m from the initial alphabets of full width at half maximum. So, let us try to understand how to obtain full width half maximum or f w h m from a spectrum. So, let us say we have an absorption spectrum. So, we are plotting absorbance versus frequency. So, first thing we have to find out what is the absorbance at nu equals nu 0, because at nu 0 the absorbance is maximum. Once we find the maximum value of absorbance, we have to find what is half of that maximum value, and once we find that half of the maximum value of absorbance, we have to find the values of the frequency that corresponds to half of the values of the absorbance. So, because we are considering a spectrum which is symmetric about nu 0, so we will have two such frequencies, one on the left and one on the right of nu 0. So, now the frequency difference between these 2 points is the full width half maximum. Now, instead of taking this frequency difference, if we take the frequency difference between nu 0 and one of these frequencies which has half the maximum absorbance, then that is given by half width at half maximum, and because the spectrum is symmetric, half width at half maximum equals full width at half maximum by 2. So, if the functional form of the line shape is known, we can find the functional form of the full width at half maximum. So, let us look into the Gaussian functional form. So, we have to evaluate this function at nu equals nu 0. So, at nu equals nu 0, f nu minus nu 0 becomes 1 by sigma root over 2 pi e to the power 0, because e to the power 0 is 1. So, this is 1 by sigma root over 2 pi. So, now that means the maximum absorbance is 1 by sigma root over 2 pi. So, the absorbance at half the maximum absorbance value is 1 by 2 sigma root over 2 pi. So, now we have to find the frequency at which the absorbance is 1 by 2 sigma root over 2 pi. So, we can write 1 by 2 sigma root over 2 pi equals 1 by sigma root over 2 pi e to the power minus nu 0 squared by 2 sigma squared. So, we will cancel out these. So, we have, or we can write ln half equals minus nu 0 squared by 2 sigma squared. So, we can also write from this equation ln 2 equals nu 0 squared by 2 sigma squared, or nu minus nu 0 squared equals 2 sigma squared ln 2, or nu minus nu 0 equals plus minus sigma root over 2 ln 2. So, now we needed to find nu. So, nu equals nu 0 plus minus sigma root over 2 ln 2. So, what does it mean? So, I have nu 0. So, this frequency is nu 0 plus sigma 2 ln 2, and this is nu 0 minus sigma 2 ln 2. So, the full width half maxima equals 2 sigma root over 2 ln 2. So, now let us look into the physical processes that lead to broadening of the spectrum. One of them is due to quantum mechanical effects. This arises from the Heisenberg's uncertainty principle between energy and time, which is given by delta E delta t is of the order of h cross. So, delta E is the uncertainty in energy and delta t is the uncertainty in time. The expression tells us that if the system survives in a quantum state for a finite time, the energy of the state in principle cannot be known with accuracy better than delta E, which is given by h cross by delta t, or h by 2 pi delta t. Now, let us think about spontaneous emission. When we excite a molecule to a higher energy state, Einstein hypothesized that the molecule will spontaneously decay from the higher energy state. If the molecule on average say decays after time tau. So, tau is the time the molecule survives in the excited state, then tau is known as the lifetime, and we can write delta E equals h by 2 pi tau, and for delta E we can write h delta nu equals h by 2 pi tau, can cancel out h. So, delta nu equals 1 by 2 pi tau. So, here delta nu is the uncertainty in frequency which gives rise to a broadening of the spectrum along the frequency axis. Thus, the spectral broadening or delta nu is inversely proportional to the lifetime. If the lifetime is short, the spectrum will be broad and vice versa. We have discussed that A is Einstein's coefficient for spontaneous emission. The unit of A is second inverse, that is inverse of the unit of time. It can be shown that A is equal to 1 by lifetime or 1 by tau. Moreover, lifetime can be affected by interactions between the quantum state and the surrounding particles, that is collisions. In the condensed phase, the occurrence of collisions are greater than that in the gas phase. As these collisions are inelastic in nature, they reduce the lifetime of the excited state. A similar case happens when pressure is increased. Increase in pressure increases the number of collisions and thus reduces the lifetime. In all these cases, the spectral line shape is Lorentzian, and thus these factors lead to homogeneous broadening. One of the most common examples of gas phase inhomogeneous broadening occurs due to Maxwell-Boltzmann distribution of molecular velocities and is called Doppler broadening. When viewed from the frame of the atom, the Doppler effect results in light energy shift or shift in the frequency of light when the source is moving either toward or away from the observer. When a source emitting radiation with frequency nu 0 moves with a velocity v and the observer is placed in the z direction, that is the detector is in the z direction, then the observer detects the radiation with a frequency not equal to nu naught, but nu which is equal to nu 0 1 plus minus V z divided by c, where this plus and minus sign is related to an approaching or a receding source. It can be shown that the full width half maxima delta nu equals 2 nu 0 by c root over 2 ln 2 k T, where T is the temperature, divided by m. So, we see that delta nu or full width half maxima of the Doppler broadening has an expression similar to what we had obtained for a Gaussian line shape. Thus, Doppler broadening is inhomogeneous broadening and gives rise to a Gaussian line shape. We can see that the Doppler width is proportional to the square root of temperature and inversely proportional to the square root of mass. For example, the Doppler width is 1 gigahertz for a UV visible transition at room temperature. However, for hydrogen the mass is small and the Doppler width is approximately much bigger, that is approximately 30 gigahertz. So, finally, I would like to end by mentioning that all these processes, the Doppler effect, the collisions, the quantum mechanical effect, that is lifetime, happen simultaneously, and thus the spectral line shape is never perfectly Gaussian or Lorentzian, but is a convolution of Gaussian and Lorentzian line shape function and is given by the void function, or the profile of the spectrum is known as void profile.